Our next speaker will be speaking about a project very dear to my heart. You've already heard a presentation about the Filecoin ecosystem today. Now we're going to listen to ChainSafe's own implementation of Filecoin in Rust by our Forest Tech lead, Austin Abell. Austin, go ahead and join me on the main stage by turning on your cam and mic.
Hey, how's it going? Can you guys hear me?
Sure can. How you doing, Austin?
Doing well. How are you?
I'm doing well. The stage is all yours, and we're very eager and excited for the presentation.
Yeah, let me just set up the screen sharing. So anyways, yeah, so as Dustin said, my name is Austin. I'm going to be talking about Forest, which is a Rust Filecoin node implementation, and talk about some of the lessons learned and challenges that we've encountered. So the three main topics I want to cover today is, first of all, is why we love Rust and how it's allowed us to improve our client, but also improve the Filecoin protocol, our challenges when implementing the node, and then also our progress as we are right now and where we want to go to in the future. So it's become very clear, and I know other people have made the comment of why multiple language implementations are important, but specifically for why we're building it in Rust and why build a Filecoin node in Rust is the two main things is safety and performance. So first, why is Rust safe? So Rust is safe because pointers and their mutability are checked at compile time, which means no null pointers, no double free, no dangling pointers or use after free. There's also no seg faults and no buffer overflows, which if you're not a developer, this may not mean much to you, but just know these are very common issues and lead to security vulnerabilities. Another big point about Rust is that there's no data races, even with concurrent programs. This is specifically important because the current trend with CPUs is that single thread performance is quite stagnant, where the number of cores is increasing. So it's very important that you write very concurrent programs, but also make sure that they're safe. And these memory and safety issues lead to a lot of security vulnerabilities. There's a few organizations here, large organizations, that have analyzed their memory and safety issues with their security vulnerabilities, and the numbers are pretty large. And these numbers definitely aren't decreasing. Just to name a few: Microsoft 70%, Ubuntu 65%, macOS 88%, and Chromium 70%. And this problem just is not solved by just having better developers. This percentage isn't going down over time, and the number of security vulnerabilities is increasing in large software projects. So another reason why Rust is performance. So a main benefit for Rust is that it gets compiled to machine code through LLVM. The profiling tools such as perf, dtrace, and valgrind just work because of this. There's no garbage collection or runtime, so that means no GC pauses, no memory overhead. And there's also zero cost abstractions, which just means it's going to optimize away any unnecessary code. There's also efficient generics, which means Rust will optimize as if there was no generics and also avoids dynamic dispatch. And specifically for this project, it is quite nice to be able to interact with the Rust proofs without going through an FFI. So for those who don't know, all the proofs for the Filecoin protocol are actually written in Rust, even though the reference implementation is written in Go. So an example of profiling, this is just one example. This is what's called the flame graph. Because dtrace and perf work with Rust out of the box, you're able to analyze what the time spent in the software, which functions that time is spent in. This is especially useful. This is especially useful in software because humans are generally very terrible at guessing this kind of thing and guessing performance of software. So it's very nice to be able to have these tools to be able to analyze and check which parts of the code are taking a lot of time. For example, this is a flame graph that the most recent one I've generated, which is syncing the node for the first 1,000 tip sets. And as you can see, a large portion of it, which I found out, which I wouldn't have guessed, is over 1/3 of it is just aggregate BLS signature verification. So that kind of indicates that we should be moving towards the more optimized assembly BLS verification that Protocol Labs has been working on. So next I'm going to talk about a few of our challenges. So I'm definitely not going to cover everything, and there's a lot of small points and learning aspects throughout the project, but I'm just going to cover three main things, which is the large data sets that are included with the Filecoin protocol, the actors, which is the state transition logic of the node, and then also some things around peer-to-peer networking and async programming in Rust and the challenges around it. So to talk about the data in Filecoin, I kind of want to start from the ground up. So the data representation of Filecoin is represented in this type called IPLD. And this structure may be somewhat familiar, or like some of the types might be very intuitive, but the thing that makes it very different, and the key point of what makes IPLD different from regular just generic value types, is that it has this link option, which is basically what a CID is. It's a content identifier, which is a hash link which links to other nodes, and this basically allows you to link all of these nodes together through those hash links, and then be able to shard the data of the network so that reads are quicker, writes are faster, and you can deduplicate a lot of data. So when you have these IPLD nodes and hash links, you generate what's called like an IPLdag, which is just a decentralized, it's an directed acyclic graph where basically you have all of the squares of the IPLD nodes, and then the arrows are the hash links to the other IPLD nodes. This is a very, very extreme simplification of what data will look like in the Filecoin protocol. So for example, you have these blocks together which form what's called a tip set in Filecoin, and those link to the underlying state, and you can represent all that data with just a few cryptographic hashes, and you can resolve any underlying data. And the benefits of this is that if there's any shared data from state transitions over, you don't have to store duplicates of this data, and you're able to, as the network size scales, you don't have to store like exponential amounts of data. This is very important also for Filecoin, because the deduplication is very important, because the state of the network is very large. The stuff that Filecoin is doing is obviously very revolutionary, but it comes with a price that the state is very large, and there's a lot of computation necessary to do the things needed to have a decentralized file storage protocol. And just to compare this data representation to ETH2, just because I think there's some interesting trade-offs and some things to talk about. First, like IPLdag is very generalized, which means that you can use it for anything. You can represent any data with it. It's also the encoding protocol is generic, so you can encode it as CBOR, you can encode it as JSON, you can encode it as protobuf. It doesn't really matter. It's also self-describing, which means if you get a hash link, you're able to not only know what the representation of the data would look like, but also which protocol it is, which encoding protocol I mean, which is very useful. There's also deduplication of similarly typed structures, which, as I mentioned, is very useful because the size of the state is very large. And then also, but the negative to this is that by default, there's less efficient proofs, because to be able to prove an element exists in this graph, you'd have to include all of the nodes all of the nodes up to the root. So to compare this with simple serialize or ETH2's data representation, it's a binary tree with 32-byte chunks, and it is very heavily optimized for Merkle proofs. The reason that this is necessary is because ETH2 has first-class support for light clients, so this needs to be extremely fast, and also allow nodes to not have to store as much data. But the negative to this is that there is some data duplication due to the fact that the types and underlying representation is built for faster Merkle proofs. And also the negative is that you have to know the underlying types of the data, so you can't just resolve and traverse any arbitrary data. You have to actually know what that data represents, which does and sometimes become a negative. So to talk about a few of the challenges with actors, as I mentioned before, the actors is the state transition logic of Filecoin. You can think of actors as somewhat like smart contracts but that are built in. So they're somewhat like precompiles in Ethereum. In this case, they're written in native Go, so the reference implementation is the specification, which kind of becomes a challenge. So a few of the challenges that we've run into when implementing these, and this has been definitely the biggest challenge when implementing the node, because it is such a large component of the network and has to be very meticulously matched, is that especially when it started, there was a very frequent and fast iteration, which is obviously necessary for the network to become what it is now. But it was very difficult as an implementer to match. It is stable now, but now there's 2 versions to maintain and also a 3rd one coming soon. And another challenge is that it's more than 20,000 lines of idiomatic Go code. So matching that is definitely very difficult. And also, as I mentioned before, the state is very large. Just to give an idea of how large the state is, the minimum pruned state of the network to be able to sync on mainnet right now is around 13 gigabytes. So whenever state discrepancies are found, it's very difficult to be able to migrate that state between implementations to be able to test and find out where the discrepancies are. Another challenge with the actors is just that the gas usage, which can cause a consensus fault, is based on the bytes read and written to the database. So it has to be very exact, and even in the case where if you read any less bytes or any more bytes, then there'll be a consensus fault, which is obviously a problem for us. Another thing is just that the language implementation differences makes it harder to do things like error handling, because there's some very idiomatic stuff that's happening, and making sure that for every code path that we have the exact same functionality was definitely a challenge. So what are the things that we did to mitigate these things? So there's a few things, and the main thing that helped us solve these issues and make sure that we have a client that does interop is one, conformance vectors. So these were language agnostic JSON test vectors developed by Raul and the Project Oni team. This has by far been the biggest help for us to be able to solve these issues, and it's definitely something great for any multi-language implementation blockchain to have, is just a lot of language agnostic test cases, because it expands the amount of which you can test at the network that you can't get from just native tests. And we're obviously passing 100% of those vectors. Another thing that's helped us kind of resolve these issues is tools to compare the IPLD state. One of them, which is state diff, which I'll talk about in the next slide, and also setting up tooling to run specific parts of the code. The reason being is that it is a very large protocol, and being able to narrow down certain sections of the code that can be identified as different and running those separate, very segregated was a way that just made it easier for testing. And then also the last point is just expanding Go and Rust testing to track database usages and serialize vectors to make sure that everything was consistent, because those are things that need to be exactly matched. And then also fuzz testing the HAMP and AMP implementations. For anyone who doesn't know, fuzz testing is basically throwing large amounts of random data at basically software to make sure that there's no edge cases or security vulnerabilities there, which we do obviously plan to expand to more things in the future. So what is state diff? So I mentioned this on the previous slide. This is a tool that we set up to help identify the differences in state between the reference implementation and our implementation. Because the state is so large, it's hard to do this. And because it is sharded, it's really hard to find the differences from just a simple cryptographic hash. So the idea is in 3 parts. So resolve all hash links to collapse the data, find the differences between them, serialize them to JSON to make them more readable, and then compare and print the differences between that JSON. So just to walk through a common issue that was run into, or a common pattern, is whenever there is a consensus fault, all you really get, and this is very consistent among other blockchain projects, is all you'll get is just a cryptographic hash of saying something under this state is different, which isn't very helpful. So the benefits of this is being able to resolve that data and compare the differences. So for example, just with those two links, you're able to resolve into state and then find exactly where the difference is. So for here, it's this one, this is one of the links that's different, and then being able to traverse deeper into that. And this is just a bug I created just to show what it looks like. And then just to see that the actual difference, you can find exactly what in state is different to be able to debug it quite quickly. And that's helped us get to an interop state. So one last thing I want to touch on is just peer-to-peer networking, which was a challenge and definitely a tough thing to do for any blockchain protocol. There are three main ways to synchronize a peer-to-peer network, generally through a distributed hash table or DHT to store key value pairs. There's pub/sub protocols to be able to publish and subscribe to events. And then there's also request response calls to specific nodes where you basically dial a node, send a request, and expect a single response back. The Filecoin does use all three of these strategies with their protocols, and it definitely makes it difficult to make sure that all these are done efficiently, asynchronous, and also make sure it doesn't block any other operation. So this has definitely been a challenge. Fortunately, a lot of the core networking stuff has been handled by Rust P2P, so that was great. And there's a lot of shared tools, and especially since ETH2 is using a lot of common things, and also Polkadot. So also another challenge was that when we started the project, async await and futures were just starting to be stabilized. So we were one of the first to kind of jump on these new futures, and kind of navigating this ecosystem was especially since it was so fragmented, was definitely tricky. And then obviously the last challenging part of mixing asynchronous code is just that you have these long-running synchronous processes, or even some that aren't, like state transitions, proofs, IO, or even shared access through mutexes, and you have to make sure that those don't block and affect any other parts of the code. And obviously this is important because you don't want anything to be slow, or else it can become a DOS vector to take down the node. So now I'm just gonna finally cover a few last points of where we are right now and where we plan to be, what our goals are for the future. So right now our project status is we're full syncing up to the Breeze fork, which is height 41,280. We are currently in the mix of upgrading from Actors V1 to V2 and supporting both. But for now, that's where we're at. We're passing 100% of the test vectors. We have all the sync protocols implemented, and we have a JSON RPC API that matches the reference implementations interface. So our goals for the future, obviously our main goal right now is interop, making sure that we can interop with mainnet and sync and validate all the blocks that currently exist is a huge benefit to the network. And then the things that we're working on in parallel and stuff that we're getting very close to as well is the miner integration and integrating with markets, which just basically means you're able to produce blocks and able to make deals with miners through using our node, and then also making sure that we have JSON RPC compatibility. So making sure that if you swap out the reference implementations node with our node, you won't be able to tell any difference from any sort of dev tooling or any usage of the RPC API. So yeah, here's the obligatory we're hiring slide. I made a little change just because I thought it was necessary. And yeah, that's pretty much it for me. Any questions?
Awesome. Thank you so much, Austin. You're an incredible engineer, and you and your team have done an incredible job with Forest. I'm sure the community is very eager to see it in production. So congratulations to you.
Yeah, it'll be exciting.
We do have a couple of questions. The first question comes from Jonathan. Do you use or have you considered using the Tokyo runtime for async Rust? And why haven't you?
Yeah, so we definitely have considered it. When we started off, we definitely liked the long-term future of async SDD. We did consider Tokyo, but it was kind of a bulky runtime, and things seem to be moving away from that, especially with stable futures. It's definitely something at this point, it's definitely something we wouldn't change. But I think we've definitely made the right choice. I mean, we've had great experiences with STD, and yeah, we don't really have any, I guess, plan to change it in the future. But yeah, we did very much consider it, and this fit way better with what we were doing.
Awesome. Thank you so much. Another question here. Where do you see the most room for performance improvement in Forest, and when do you think we can start seeing Forest releases?
Yeah, so releases, I think releases are definitely going to, well, I'll just answer that second part first. I think releases will definitely come once we are syncing up to mainnet. We do have a few things we want to resolve, which should be resolved pretty soon, but hopefully we can start to see releases within, soon. I don't want to give an exact date. And as far as performance improvements, as you can see from Flame Graph, like I think the main improvement right now is just optimizing and making sure that the BLS signature verification is as fast as possible, and making sure that it's parallelized whenever it can be, which it pretty much is right now. But as you can see, it still takes a very long time. So I think targeting that is definitely the biggest thing. But there's still like small wins here and there, and we definitely want to be going a lot more into profiling in the future. So once we finish these immediate goals of interop, we're going to move definitely very quickly towards that.
Awesome. Thank you so much, Austin. I know you're a busy guy. Thank you for taking the time to speak with us today.
Thanks, Dustin.